Have you ever wondered how a drone can hover perfectly still in air or fly a mission all by itself? Behind every stable hover, every smooth flight path, and every autonomous mission lies a hidden brain called the autopilot system. This system runs thousands of calculations per second. It reads data from sensor, estimates where the drone is in space, and sends precise signals to the motors to keep it flying. In this video, we are going to go deep inside the brain. I will explain how drone autopilot system works, from sensor fusion with Kalman filters to PID control loops to navigate algorithms, and finally how three of biggest open source projects, ArduPilot, Pix4, and Paparazzi UAV, implement these ideas in different ways. Let's get started. An autopilot system in a drone is a tightly integrated combination of hardware and software that enables the drone to fly stably, carry out pre-planned missions, and in some cases operate entirely autonomously. At the core of this system is the flight controller, a compact computer equipped with processors, memory, and various sensor inputs. It collects real-time data from onboard sensors such as gyroscope, accelerometers, barometers, and GPS to maintain flight stability. Running on the flight controller is the autopilot firmware, a specialized software that interprets sensor data, executes flight logic, and communicates with other systems. The firmware handles everything from basic stabilization to advanced mission planning and autonomous navigation. Together, the hardware and software form the brain of the drone, making autonomous flight possible. You can think of it like this. The sensors are the eyes and ears of the drone, the flight controller is the brain, and the motors are the muscles. Without the brain, the drone would just fall out of the sky. So now we know what an autopilot system is, the brain of the drone. But just like our own brain, it can't work in isolation. It needs senses. For drone, those senses come from sensors. Let's take a closer look at the key sensors that make autonomous flight possible. The most important is the IMU, or Inertial Measurement Unit. Inside, it has an accelerometer to measure linear acceleration and a gyroscope to measure angular velocity, basically how fast the drone rotates. Together, these act like the drone's sense of balance. Next is the GPS, or Global Positioning System. This provides global position, latitude, longitude, altitude, as well as velocity. You can think of it like giving the drone its own version of Google Maps. The barometer is used to measure air pressure, which is then converted into altitude. This helps the drone to hold a steady height, though it can drift with changes in weather. And finally, the magnetometer. It measures the Earth's magnetic field and uses that to calculate heading, essentially working as the drone's digital compass. No single sensor is perfect. The IMU drifts, GPS is noisy, the barometer drifts with pressure, and the magnetometer can be disturbed. The autopilot needs a way to merge all these data together in real time. The algorithm that makes this possible is called the extended Kalman filter. This algorithm runs in real time, constantly predicting the drone's position using a mathematical model and then correcting that prediction using incoming sensor data. The result is a smooth, accurate estimate of the drone's position and orientation, even when sensors are noisy or drifting. Once the autopilot knows the drone's state, it has to keep the drone stable. This is where control loops come in, usually PID controllers. A PID controller is just a smart feedback system. Imagine you are driving a car and want to stay at fixed speed. If you go slower, you press the gas. If you go faster, you ease off. That's proportional control. But what if there is a hill? You will keep pressing more gas over time. That's integral control. And if you see the car speeding downhill, you react earlier. That's derivative control. In other words, a PID controller constantly compares what you want with what's actually happening and adjusts it in real time to minimize the difference. A PID controller has three parts: proportional, which reacts to the current error; integral, which sums past errors to correct long-term drift; and derivative, that predicts future error based on rate of change. In drones, PID controllers don't just work in a single layer. They are arranged in what we call cascaded loops, where one control loop feeds into the next. At the inner loop, the controller manages angular velocity. That's how fast the drone is rotating around its roll, pitch, and yaw axis. This is the fastest loop, running hundreds of times per second, and it directly commands the motors. The middle loop manages the drone's attitude or orientation in space. Think of this as keeping the drone level at the angle you want. The attitude controller sends commands to the inner angular rate loop to achieve those angles. The outer loop controls position and velocity, where the drone is in space and how fast it's moving. If you tell the drone to move forward 10 meters, the position controller generates the desired pitch angle, which then gets passed down to the attitude loop and finally to the angular rate loop. Each outer loop sets the target for the inner loop. This cascade makes the drone precise at the slow or large movement, while still being extremely stable and responsive to fast disturbances. So PID controllers are the muscles of the drone, constantly adjusting motor speeds to keep it balanced and on track. But stability alone isn't enough. To fly real missions like waypoint navigation or obstacle avoidance, drones need something more, which is called navigation and autonomy algorithms. Let's look at how they work. To fly useful missions, drones need to actually go somewhere, and that's where navigation and autonomy come in. First, the waypoint following. The drone can be given a series of GPS coordinates and it will fly from point to point using simple guidance laws like proportional navigation. Next, path planning. In the real world, the sky isn't empty. There are buildings, trees, and no-fly zones. Algorithms like ISTAR or rapidly exploring random trees help the drone find safe, collision-free paths through complex environments. But what if GPS isn't available? That's where SLAM or simultaneous localization and mapping comes in. Using cameras or LiDAR, the drone builds a map of its surroundings while figuring out its own position inside that map. This allows drones to fly indoors, underground, or in GPS-denied areas. And of course, drones need failsafe. If GPS is lost, they can return to their takeoff point. If battery runs too low, they can automatically land safely in a state of crashing. Some systems even go further by adding companion computers like Raspberry Pi. These handle advanced tasks such as real-time object detection, target tracking, or even swarm coordination, while the main autopilot focuses on stability and flight control. In short, navigation and autonomy are what transfer a drone from just a flying machine to a truly intelligent robot.